Hello, Providence Chemistry. We're back again. This is day 2. And I'm going to read the same verse I read yesterday just to hammer it home. I love the Lord because he has heard my voice and my pleas for mercy, because he inclined his ear to me. Therefore, I will call upon him as long as I live. God, thank you that you love us that much. Okay, guys, we're going to go ahead and get this packet out again. And today we're going to go number 36 to 40. So if you don't have that out, go ahead and get your calculator, get this pencil, and stop this thing if you need to. All right, before I do that, let me go ahead and show you Boyle's law to remind you what they are. I have here a balloon, and I have that little chip crisper deal. And I'm going to go ahead and I'm going to pump the air out of this balloon, and I'm going to hold it up for you. See if I can get you to see it. How about that right there, huh? Now watch the balloon as I pump. I bet you can't see it. Go ahead and try it this way. A little better. This box will hold up. Sizably bigger. Because Pascal says, Boyle said, if there's less pressure, then the volume of the trapped gas gets bigger. They vary inversely. Let's go ahead and put more pressure by letting the air back in. You see that the balloon shrinks dramatically. And let's heat it up. What's going to happen? It gets bigger in my hand immediately. And that's a direct proportion. As the temperature of the trapped gas goes up, the volume of the gas gets bigger. Okay, and then the third one is that was that good old pressure cooker. When you heat up the gas, creates greater pressure if the volume is constant. And then tomorrow, I'm going to show you one more demonstration about the fire syringe. The one more thing here today, this is an example of what air pressure can do. So you got these little devices that Tom Cruise likes to use, and you pull on them. They can't come apart. Okay, but if you just simply do this, you come right, you just let some air in. Okay, Mission Impossible, of course, you know that. Number 36 on your review goes like this. What's the density at STP of nitrogen dioxide gas? Molar mass 46 in grams per liter. Well, you all know that density is equal to mass divided by volume. But if it's at STP, let's go with a molar volume. And the molar mass for this gas is NO2 is known as well. So let's go ahead and use the density at STP is the molar mass of nitrogen and 2 oxygens. Nitrogen is 14 and 2 oxygens is 32. And that gives us 46 grams per mole. And the magic number for molar volume at STP is 22.4 liters per mole. Per mole. Per mole cancels, and you get grams per liter, and that's the density, 46 divided by 22.4. And that's 2.05 grams per liter. And that is what we expected. Number 37, what's the volume? This looks like it only has one volume and one pressure. And so I'm thinking this is the ideal gas law. So we're going to do 37. And the volume of 2 grams, huh? So we've got a mass of 2 grams. We've got molar mass of 76.15. And do you know what mass divided by molar mass gives you, right? Mass divided by molar mass gives you the number of moles. And that's the letter N. So 2 divided by 76.15. 2 divided by 76.15. 0.026 moles. Okay, and then 70 degrees Celsius. Plus 273. What is that? 343. Okay. And we're going to cross that off so we don't mess up. The next thing is 726 millimeters of mercury. But I like to use atmospheres. You don't have to, but it's just a different constant of proportionality, ideal gas law constant. And you just have to look in the book and find out what it is. I'm going to convert it to atmospheres. 760 millimeters of mercury is 1 atmosphere. And so 726 divided by 760 is 0.955 atmospheres. That's the pressure. Once again, you don't have to convert it, but I love to know that my constant that I'm going to use is 0.082. And that's all they give us. So let's go to PV equals NRT 0.955. Volume is what we're looking for. N is 0.026. Moles. R is 0.082 from the table in your book. And the temperature is 343. We'll divide both sides by 0.955. You're going to get volume in liters because of that ideal gas constant that I use, 0.082. So let's see if it works. 0.026 times 0.082 times 343 divided by 0.955. I get 0.76, and I got 0.765, so they got 0.77, which is rounded off correctly. Liters. The next one is number 38. Looks like an equation, but it isn't that hard. So don't panic. Here we go. We've got CaCO3 plus, no, yields. It's decomposition. CaO and CO2. Okay. How many grams of calcium carbonate? That's where we're headed. Must be decomposed to produce 5 liters. Carbon dioxide, that's where we start. And notice that it's at STP. If it's at STP, then we know that 1 mole is 22.4 liters. And we can cancel liters, and we can calculate moles of carbon dioxide. And that would be 5 divided by 22.4 equals 0.223. Moles of carbon dioxide gas. Now we got to go from there and compare moles with moles. And then we got to convert moles into grams. This is going to be a 2-step. So it's going to be 0.223 moles of CO2. Moles of CO2 go down here, so it'll cancel. Moles of CaCO3 go up there because that's at the end of the arrow. Moles of CaCO3 go down here, so it'll cancel. And grams CaCO3 go up there because that's at the end of the arrow. That's where you're headed. Okay, let's go ahead and fill in some numbers. It looks like this properly balanced equation is 1, 1, and 1. So 1 mole of CaCO3 to 1 mole of CO2 is the mole ratio there, and these cancel. And then that right there converts to 1 mole of that. It says in the problem is 100.09. Let's just call it 100. So take that times 100. Oh, I can do that by myself. 22.3, that's 2 bunny hops to the right when you're multiplying times 100. 22.3 is the right answer. Okay, 39. How many times greater is the rate of effusion of fluorine gas? Okay, we're comparing fluorine gas, F2, to bromine gas. So the rate of effusion, I'm going to call it the velocity, and that would be the velocity, is equal to the square root of the molar mass of Br2 to the square root of the molar mass of F2. You guys remember that's the equation. And what do they want to know? How many times greater is the effusion of fluorine? So what they want to know is this number right here. So to find all of that ratio, how many times greater this is than that, all you have to do is calculate this over here. It's this part. So we'll do that. The square root of the mass of Br2. The molar mass of Br2 is 159.8. Let's call it 160. To the square root of 38. all in your problem. I didn't even have to have a periodic table, fortunately, because I forgot to get one out. And so all I'll do here is I'll go square root of 160. Where's my square root button? There it is. 12.64 divided by the square root of 38. And that equals 2.05. And your answer is 2.05. Times faster. So fluorine, because it's smaller molar mass, will diffuse twice as fast as this bromine, which is a bigger molecule. Okay, let's move on. Number 40. Oh, we got a rust problem here. I'm going to try to get away with not washing this. I'm going to go over here. We got rust, and we're going to combine iron with oxygen to produce rust. Iron is Fe, oxygen is O2, and we produce iron 3 oxide. Iron oxide plus 3, that's -2, crisscross, 2 goes there, 3 goes there. This is written correctly, that's written correctly, and now that's written correctly. So all we need to do is step 4. And step 4 says 1 iron, 2 irons. We got 2 irons. It says 2 oxygens, 3 oxygens. Least common multiple is 6. So let's get 6 of them over here and 6 of them over here. And now I messed up my iron, so I'm going to have to fix that by changing the 2 into a 4. Okay, that's the properly balanced equation. We want to know how many grams of rust can be produced. Grams go on top. Excess of iron and 11.2 liters of oxygen. And here it goes again, STP, that's the magic phrase. So what's the magic number? 22.4 liters in every 1 mole. And so they're at the same, it's a STP. There you go, cancel liters. Oh, I can do that in my head. That's 1/2, 0.5. So we have 0.5 moles of oxygen. Compare it to moles of iron 3 oxide, and then change that into grams of iron 3 oxide. 2-step problem. So here we go. We're going to go ahead and take 0.5 mole of O2. Moles of O2 go down here. And I need a new marker. And 1 mole of O2 weighs 32 grams. And then we're going to put grams of O2 down here. And we're going to moles. Wait, hang on. Grams of O2 because they cancel. Wait a minute. I messed up, guys. I didn't follow my arrow. 0.5 moles of O2. So moles of O2 go down here, so you can cancel. What's at the end of the arrow? Moles of iron 3 oxide. About that. Moles of iron 3 oxide go down there, so they'll cancel. And grams of iron 3 oxide go up there. because that's at the end of the arrow. And we've got moles of O2. This has got a 3 in front of it, and this got a 2 in front of it. And 1 mole of this stuff weighs, oh, we got to add that up. Did I say what it was? No, of course not. Two irons at 55.8. 2 times 55.8 plus 3 oxygens times 16. 159.6. Let's call it 159.6. Okay? So now let's go with that number times 2, and multiplying backwards, times 0.5 divided by 3. And I get 53.2, and 53 grams is the answer. So there you go. Now, do the quiz online on LMS, and you guys have yourself a happy day. God bless you.